Well, at this time, I was a little boy. I'm born December 1959, so I was 10 years old at this time. But I had already gained an interest in computers, and especially when I got a copy of this Life magazine handout, and it was basically explaining how a computer works. With on the left-hand side, you see basically a railroad track representation of the different registers and the units in a computer and memory, and then the trains would pass the bits around, and was very, very illustrative and educational. And then obviously on the right-hand side, you see a beautiful picture of an IBM 360 machine, which is which is basically the first computer that used a form of integrated circuits and hence could be relatively small for a very powerful machine. So I quickly turned out to be a computer fanatic. So at age 13, I was designing little circuits that could do computation, such as on the left-hand side, a self-designed 4-bit adder circuit. Adder means it adds two numbers. And this was done using electromechanical relays. And you see myself on the picture. I think I was 15, not a picture. So there are no pictures of when I was 13, not that I could find. But what I did do is I often went to the RAI Conference Center because that was around the corner from where we lived. And actually, I was a small boy, so I would go to the entrance and say, "Yeah, sorry, my father is on one of the booths. Can you let me in?" And they generally let me in. And so I was walking around and looking at all the equipment there and staring at all the beautiful stuff. And I do remember seeing this computer, the Data General Nova. And I even have evidence because I brought a brochure that I picked up at the RAI Conference Center of this computer. And this was the first affordable 16-bit mini computer. And affordable meant something like £10,000. So, and I was very much impressed by that. And I obviously dreamt on, and I started built on and on and on. And but the reason why I'm mentioning this Data General Nova, and actually I can give this a swear. I'll put it here, yeah. Is because the Data General Nova is actually the computer that was chosen to be used by EMI and Hounsfield in the Mark I CT scanner. Now, the Data General Nova is a 16-bit computer. Its clock speed is in the order of less than a megahertz. And it could reconstruct a single slice of 80 by 80 pixels in about 5 minutes. And the pictures that you see here are taken in the Science Museum here in London. So here you see a 1975 leaflet of the EMI scanner, basically showing you the scanner, some of its images, very nice images, but also the computer cabinet, the viewing unit, and the line printer, because actually some of the output of the scanner was a printout of the CT values on paper. But I didn't know about all this. I was still in high school, and then later I studied physics, and I didn't study physics very much because I was always at home building my own computer. I got my hands on an 8080 chip, which is an 8-bit microprocessor, and built with various new and recycled parts a computer around it. And if you look at this picture from our sleeping room, what is obvious is you see quite a large monitor, which is actually a serial terminal. And I'll come back to that serial terminal in a second. The computer is built in a nice box, which was actually recycled from the cellar of the hospital. It was a different bit of equipment. Hi there. And you see a teletype on the bottom, which I bagged from the university, which were throwing them away. And I repaired them, and I hooked everything together, and I could do my computation on that computer. And the interesting thing is, when I moved to the UK 10 years ago, I was stuck with this stuff, and I thought, well, what shall I do with it? So actually, I decided to donate the terminal to the National Museum of Computing at Bletchley Park. And if you look in my picture, you see two little scratches in the red line, and those are the same two little scratches on the terminal in the National Museum of Computing. It's actually sitting there. This is exactly the same terminal. And I downloaded this picture last week, and I was very pleased to see that I actually got the monitors working, because there is information on the screen. And so I remember repairing it. This is a very, very early terminal. I think in the order of 1968, it used DTL logic, if that says anything to you. And the storage was not on chips because the memory chips didn't exist yet. The storage was done in what is called an acoustic delay line. So there is a very long wire that is sitting at the bottom of the box, and you put sound in on one end, and 20 milliseconds later, the sound comes out at the other end, and then you put it back in, and in the sound, you put all the bits of what's on the screen. And the funny thing is, if you have the monitor on, and I don't know whether it'll let you try it, but if you tap the side of the monitor, you get random characters on the screen because they go into the sound of the delay line. So this is a very, very early terminal, and I think this is the earliest terminal that I now have in Bletchley Park. And there are two. One came from my collection, the other one came from the hospital, because our hospital in Amsterdam, the Netherlands Cancer Institute, had one of these terminals in the cellar, and I sent that to them as well. So we need a computer to do CT reconstruction, and the core algorithm of CT reconstruction is back projection. So basically what back projection entails is that you draw a line from every detector where you're measuring the X-rays transmitted for the object back to the source, and you do that for every angle of the scan, and basically means that where all the lines come together, you see where the object is, at least in principle, and it definitely works if the object is like a nail or a single point. One of the problems of this back projection algorithm is that it's very time consuming, and I'll come to that. The other problem is that you get a snare out, because where all these lines are converging, the intensity gets higher and higher until you have a very high intensity at the point. So if you do this for a complex object like a human brain, then the image is completely unusable. So Godfrey Hounsfield solved this by using an iterative reconstruction algorithm, which is very, very advanced, and actually has only been introduced in clinical practice in the past few years. But a colleague of his, Christophe Lemay, came up with the idea of compensating for the blurring of the line by basically subtracting the information from the surrounding lines from each point. And so basically using a filter, and you can see here the filter constants, which I actually typed into a program, and they turned out not to work. So there is something wrong with these filter constants in this book. But yeah, but if you use this and you do the filtering, then you get a proper CT image where you don't have this enormous washout. So I have always been interested in computing, and when I found on eBay a Data General Nova computer, I jumped on it and I offered 250 quid, and I won the auction. And this is when the computer arrived at my home. It's a 19-inch rack. It weighs about 25 kilograms. And this is a small sister computer of the computer that EMI used in the first CT scanner. So my computer has 4 slots. It's small. It has a 1200 nanosecond cycle time. And I got a processor board and a memory board. And later on eBay, I found another board that I got shipped from America, and I paid 5 times more for shipping than for the board. And I actually got a serial port, which is a complete board from somebody in America who is still maintaining and working with these kind of computers, because apparently they're still in use. So in the CT scanner, we have a bigger computer with 12 slots. It has a lower type number. That means it's faster because it's an 800 nanosecond cycle time. The processor comes on 2 slots because it's faster, and it has 32 kilowords of memory, while I only have 16 kilowords of memory, and a word here is 16 bits. So I have 32 kilobytes of memory, and EMI had 64 kilobytes of memory in their computer, and that was the maximum that this computer could take. So what does it look like inside? You have the processor board. It's not a microprocessor, but it's basically a processor made from, well, not discrete components, but from very simple TTL logic chips, where the chips would have between 10 and 20 gates per chip. And the most complex chip is in the bottom here, and that is the arithmetic chip, the 74181. And there are some memory chips there, 74 184. No, I think. What the trick that they use is to make the instruction set incredibly simple. And so this is like a reduced instruction set computer, and it turned out to be incredibly efficient. For about a decade, Data General Nova was the fastest computer on the planet, basically. Well, the memory is another thing. There were no memory chips. So how do you store information? Well, this is on a core memory. The cores are sitting below this black panel, and you have lots of electronics around it to drive the cores. And I have a zoom in of that. So if you look inside, a core memory is basically a woven mat of zillions of wires. And at the crossing of the wires, you have a tiny little magnetic core. It's a permanent magnet. If you break one, it sticks, it's a magnet. But if you put enough current through two wires, you can flip the magnetization of the core. And it's a permanent magnet. It will stay like that forever. Until you put the reverse current through it, and then you can make it flip the other side. But if the current flips, then you induce a signal. If the magnetization does not flip, then you introduce no signal. So you can read out the signal that is in these cores, and you can do that with a computer from 1972, like 40 years later. So I got this computer to work, and I started building the bit that I was missing, and that is the front panel. And I'll come to that front panel. Old computers have switches on the front, and you can use the switches to program the computer with individual bits, bit by bit. It's very time consuming. But my computer came from a phototypesetter. It didn't have the front panel because it was embedded in another machine, and they didn't need to have to expose that bit of the computer. So I first built one with loose wires and stuff, and I made it work. But then after a while, it fell apart, and I wanted to give a lecture at a computing conference. So I built a new front panel from scratch with a nice printed circuit board and everything. And that's what you see here on the right. And we'll see it again. So now my question is it possible to do CTE reconstruction on my Data General Nova? And obviously Hansville could do it, and Stephen Bates, the programmer. So I should be able to do it. And I tried to do it for my conference 5 years ago, but I ran out of time. And I thought, well, for this lecture, I'm going to do it again. I'm going to implement CTE reconstruction on a 52 years old computer. And well, the algorithm is listed there, but and it's actually interesting. You think there are lots of sines and cosines in CTE reconstruction, yeah, because you need to look at the angle and get project all the lines back. But it turns out to be that the sines and the cosines are constant, and you can just put them in a table. And then the multiplications that are in the geometrical equation are not necessary because you're stepping pixel by pixel, and so that's a constant distance, and so that actually just becomes an addition. So the actual algorithm, if you look here in the inner loop, is just adding something to the radius and then accessing the signal under where the radius is and adding it to the image. But for a CT reconstruction, as the EMI Mark I used it, that has to be done 1.2 million times. And you can imagine that it's time consuming. So in the book, there is a little bit of code. I wrote Hounsfield's, but it's probably Stephen Bates' code that was running on the EMI deck. And this was done in assembly language. And if anybody knows a little bit of C, this is the corresponding C code. You basically write the output, the number on the input, but you index it on a number that has to be a fraction of a pixel. Because if you're stretching or compressing a line of information, that's the basic operation, you don't wind up in entire pixels. So you need to do this in subpixels, and I do that here by dividing my offset by 2 to the 16th, which is equivalent to shifting right 16 bits. And actually, because the Nova is a 16 bits computer, basically means you have one register in which you keep the low bits of where you are, and one register where you keep the high bits, and you're just using the high bits to index the computer. And so basically you're stepping through the input array on non-integer locations. And in my bit of code, so that I wrote over the Christmas holiday, it takes 19 times 1.5 microseconds to do one voxel, and that needs to be done 1.2 million times. So I have Data General Nova at home with the lights and the switches. So I built my own, and that own front panel that has a Teensy. This is a Teensy. It's a tiny little microcontroller. It has an ARM processor. It's actually really fast. This computer is way faster in terms of storage and speed, and way cheaper than the Nova. But this is what is running the front panel. This is toggling the switches on the front panel. So if you want to have a look. That Teensy is connected to a Raspberry Pi that is connected to the internet. And then there are a number of anachronisms. I have a little LCD display there, which I can display information. I have a little screen where I can show the image, and have a keypad, which is also an anachronism. So basically, and now it becomes interesting, I have this computer sitting at home, and this computer is actually being monitored right now by a webcam. So hopefully this is going to work. So I have here a login to my Raspberry Pi. So the Raspberry Pi is sitting, there's the white box sitting in front. And then here I have a browser. And now I'm going to turn on the webcam. Yes, this is my Data General Nova sitting at home. And now hopefully I can turn it on without blowing any fuses. So I need to find a command to turn it on. And actually, Dennis, my student, is sitting at home right now and is listening to the talk. So if we have a power loss, he can trigger the fuse. But I'm turning it on right now, and we see the lights go on, and the computer is actually running. Well, it's not running, it's on. And this computer can do different tasks. But let's start with CT reconstruction. So, but first I need to make contact with the computer, and I do that by using a serial terminal. And I apologize for the small. Oh, this is the wrong one. I need to go to port number. This one. Okay, now I have contact. Let me see if I can make the font a little bit bigger. Setup. Where? Change settings. Window appearance. Where is the font? Here, font. Let me make it a little bigger, then we can see what I'm doing. Okay, 14 points, apply. So what I'm now doing is I'm talking to the Teensy computer that you're now passing around, and the Teensy computer can do things to the computer. For instance, it can look inside. So I can, for instance, look what is on a particular memory location. And whenever I give a command to the Teensy, it will toggle the switches, which are not there, and you'll see the lights briefly blinking. Hopefully. Do it again. Very briefly. So it's now reading the information that's in the computer, and there's just a lot of words, and you can actually disassemble code that is in there, and then you see a little bit of assembly code. And this is the CT reconstruction code. And I just wanted to run it and so I'll do that. So I'll start the CT reconstruction code. And now, so what you're going to see is you're going to see all the lights blinking very fast, because you see the data bus and the address bus of the computer that is connected in real time. And there is a little light that says when the computer is running. And so when the computer is running, the light is on. When the light is off, the Teensy is taken over. And for instance, it's used to read information or to display an image. So let's give it a go. So you can see the lights blinking very fast, and you can see the first back projection appearing on the screen. And once every 16 projections, it updates the CT reconstruction this far. And I think it's working. There's a thermometer on there because it's a little bit temperature sensitive, but I think it's not crashed yet. And actually, I hope. Did it crash? Or did I lose connection? It crashed. Well, we just started again. So the computer is pretty good, but it is a little bit temperature sensitive. So you can see every projection takes a fraction of a second, and that is the total time. And in that fraction of a second, it does 6,400 voxel operations to do all the back projections. And let me see if it makes it through to the end now. Okay, 62, 64, it's redisplays, and you can see that a skull is starting to appear on the image. And those are the last 10, and now it's done. So I did 90 projections, so that's half the number of full projections that Hans would use in the EMI, and took half a minute, and that's the speed that I can get. Now it is a general purpose computer, so I can also, for instance, load the original basic interpreter, and then start it. Yes, this would look like, this is exactly how it looked like in 1971. So I could say, for instance, print I, and then 20 go to 10. And then if I do a run, run, then you see all sorts of zeros. Well, this program is not very interesting. So I can list the program, and I can change, for instance, like in line 15, I can say let I equals, equals, where's the equals? It's this Japanese keyboard. Okay, 15 let. I could do it before, but it's more difficult if you're in front of an audience. Equals here? No. Where's the equals? It's here. Let I equals I plus 1. Now I need to do the capitals. Plus 1. Almost. 15. Thank you. And there is no backspace. Okay, there we are. And now we have a program like a list. It's actually really hard to do this in front of an audience. And now I have a program that counts up numbers. And by the way, you can see all the lights going on because they're blinking really, really fast. And if I stop the process, you see the lights freezing. So this is a very, very old BASIC interpreter. The original BASIC was from 1965. This is 1971, way before Microsoft, running on a Data General Nova computer from 1972. Okay, so let's compare the EMI Mark I to my setup. Well, I have a slightly slower computer. I have less memory. I don't have a lot of storage. I have a tiny little display, but still I can do a reconstruction in 1 minute, while Hounsfield's iterative reconstruction used around 5 minutes. I also have a simulator, and because if you want to do this at home, obviously you don't want to have a big machine. So this thing actually simulates the complete Nova. And if somebody is here for the Science Museum, I'd like to put one next to the original CT scanner. I'm happy to provide it. But yes, so if you push the button, then you can select what you want to do. For instance, a filtered back projection. And I don't know whether you guys could see that online on the thing, but yeah. So this does a complete simulation of the Nova computer and has all the software on it, it has about 40 pounds worth of stuff. So anybody can download the software from the GitHub and play with it. And let's show that again, but then on a movie. So here you can see the reconstruction going on and the lights blinking on the tiny little display. So the top of the display emulates a teletype. The middle display emulates the computer with the blinking lights, and the bottom side of the display emulates the CT display unit, which was of a similar resolution, although it was a little bit bigger. Okay, and well, I'm going to pass this through. Hold the back of the rotary key. Put the rotary key, you can select an option and then do it. See if somebody breaks it. Okay, I started in radiotherapy in 1982, and the CT scanner already existed quite a bit of time. In 1981, the first one was installed in our department, a Siemens Somatome CT scanner. The slices were 256 by 256, and they actually came on these kind of floppy disks. So if you, these are 8-inch floppy disks, and these floppy disks stored a couple of slices, and you could pass this around as well. And I was asked to work on verification of radiotherapy. And basically, verification of radiotherapy was done with film. You put a film in the treatment beam, then you hope you see some shadows of the patient in the megavoltage beam, but the beam is really, really high energy. It goes straight for everything. You don't get any contrast at all. So it's very difficult to do. So I was tasked to make a digital detector to do this. And I succeeded, so I developed with my colleagues a compact megavoltage imager, which is based on liquid-filled ionization chambers. And you can see myself as photo model in the publication. And you see one of the images, and this is a very early images from 1986, so the second clinical image that we ever took. And that image was of a breathing lung cancer patient. And we could take movies of patients because we had a digital camera all of a sudden. But we could do nothing with it because PowerPoint didn't exist. There were no video monitors. We could record it on a tape and then bring it to here and then play the tape somewhere on a tiny little screen. That's as far as we got. So I was actually a computer enthusiast, but I told my boss, well, let's buy an IBM PC. And he said, well, it's a bit too expensive. So we didn't buy an IBM PC. We built our own PC from scratch. So that was not expensive. But that's what we did. And that PC consists of an 8086 CPU. And actually, I restored it. So if you're in Manchester, you can have a look at this computer and you can play with it. I'm now loading an image from hard disk. Although the hard disk that came with the computer is broken. So I built a tiny little microcomputer board that's sitting right there, which contains another TNC microcontroller. And now you can see it is displaying an image of a common household object. And if somebody can guess what it is, then I will give them a beer. Okay, so this is computing in the mid-80s, just before the PCs arrived. Now, in 1990, the software was kind of finished, and that software came in clinical use. And the picture in the middle was taken in 2015, the year that I left NKI. And this is Ron Veilbrief using exactly the same software 25 years later. So that software was in use for 25 years. And this is a simulator running DOS and the entire software package again on a TNC microcontroller. So I can show that later, but I can run a little bit of the movie, and you see. If I don't know whether anybody can remember a DOS PC, but it enters a C prompt, and then you type a command, and then it is starting the software that we wrote specifically for the megavoltage acquisition. And I'm still a Pink Floyd fan, and my colleagues had made this lovely design of the background, which is a wall, and so hence the wall on the background. And from there you can load and display your images. And actually, I finished the simulator last year, and the simulator the DOS simulator I could just download from the internet. So other people had done that, but I had to write a specific video driver to make it display the images in the bottom. So I used the software tools that were still on my restored hard disk to compile that video driver with tools that I used 30 years ago, 40 years ago, and now it's loading an image. It takes a little while. Yeah, so toys. So megavoltage imaging allowed you to basically do a two-dimensional verification of the position of bone and air, anything else you couldn't see. So in 1997, David Jeffrey and John Wong proposed actually to integrate CT on a linear accelerator. And we entered a collaboration with them in the year 2000. And we got a prototype from Elekta. And that prototype came without any usable software. So we wrote our own. And actually that software then was licensed by the company Elekta and sent out in the software. We have, with the product, there are 16 of these in Manchester, thousands of these units worldwide. And I'm pretty sure that more than 10 million people have been treated with that software. But this is CT, cone-beam CT, and CT reconstruction is slow, yeah? So when I submitted a paper to MICI, I got a bloody 1 minute poster because they said, well, you can never do CT reconstruction because it takes an hour. Well, I've proven them wrong. So basically, I needed to develop fast cone-beam CT reconstruction. And cone-beam reconstruction is very much similar to CT reconstruction, but rather than doing it slice by slice, you do it for the entire volume at once. So you have like 300 projection images, X-ray images of the patient. You do a log and filter, the same thing as you do in a regular CT. And then you do a back projection, but rather than doing it to a single slice, you do it to a whole volume at once. But wait a second, this is not as simple because you have divergence and stuff. So this is mathematically much more complicated, isn't it? But I managed to do it with write a loop that did it in 3 nanoseconds per voxel and did the entire reconstruction in 16 seconds. And the trick is as follows, because the scanner is rotating around the patient and you have perspective because of the magnification. But there is one single axis where there is no perspective, and that is perpendicular to the rotation axis. Because there you're always looking at the same bit of anatomy, and its magnification doesn't change. So if you are projecting along the vertical lines, then you don't have any perspective, and you can actually use exactly the same little sub-pixel stepping loop as I used in the NOVA algorithm, which I actually copied from this software because I wrote this first. So that makes the calculation very simple. And the other thing is that modern CPUs have a so-called cache memory. That means that there is a little bit of memory that if you access it frequently, it's really quick. And as soon as you go out there, it's slow again, and then it needs to reload that bit of memory. So basically what I did is I took my patient and cut it up in like standard spaghettis, and I took little packages of spaghetti that were just big enough such that its projection onto the projection image fitted within the cache. And then if you would loop these blocks, then you wouldn't have any cache misses, and that makes this thing run at 3 nanoseconds per voxel. And so that was in 2003, and we're talking here a Pentium 4 processor or a Pentium 3 processor. So this is a while ago. And I haven't mentioned interpolation at all. This is a bit nerdy, but if you do the back projection, you can imagine that if you take a pixel or a signal from a detector and you put it on the nearest voxel in your image, it's going to be very steppy and blocky. And that means you get a lot of artifacts in the image. And so what you can do is rather than getting the signal from a detector, you want to interpolate between the detectors and get a mixture of the two signals of the two detectors, where you get most of the signal from the detector which is closest. But that takes an enormous amount of time. That in my cone-beam CT reconstruction, that would more than double the reconstruction time. So the trick that I use is actually to say, well, actually, I don't need to interpolate while I'm back projecting. I can interpolate the image beforehand. So what I did is I took the image beforehand with coarse pixels, and then I interpolated by a factor of 2, which doesn't cost any computation at all, because it's just the pixel in between is just half the values of those subsequent pixels. So you can do that with very little instructions. And it turns out that the image quality is almost as good as full interpolation. And if you want to go better, you can go up to a factor of 4 pre-interpolation. But in the clinical software, it's using this factor of 2. And that adds only 7% to the time, while it recovers most of the image quality. So then we had this reconstruction algorithm, and we had our clinical prototype, and then the question is, how were we going to put this into the world? And the hard part was actually just to throw away all the functions you really don't need. So the left picture shows you the user interface of our research software, and everything that we didn't need has been crossed out, which is pretty much every button. There's no buttons left. And so what we sent out was a system with only a few buttons. You push a button to scan the image, push a button to match, and push a button to shift the table. That's it. And that worked. And we thought Elekta would be selling a few of these per year, but it turned out that all the linear accelerators that were made from that point on were pretty much shipped with Chromium CT on it. And we went even further. And 5 years later, we released a version where there was 4-dimensional imaging implemented, and such that you can visualize the breathing of the patient as a movie loop. And again, we try to make it as simple as possible, just a few buttons, nothing complicated. And so let me show you what that looks like. And maybe I should now turn off my webcam because that's taking a little bit of time, actually. Okay, so where is it? Here, it's here. Now I'm opening a patient. So what we're going to look at now is a Chromium CT scan of a patient made on a linear accelerator. And we're going to compare that to a scan of the patient made for planning. So we have a proper CT scan and a Chromium CT scan overlaid on top of each other. But in this case, the Chromium CT scan is 4-dimensional. And I can just stop that for a second. And then we can flip between the two scans. And basically what you can see is that nothing is in the right place. It is very, very difficult to put a patient back on exactly the same place on the table because you use tattoos on the patient's skin, but those tattoos are very wobbly because the skin in the abdomen is very, very soft and easily moves and when the arms move. So nothing is in the same place. So now how do you know how to treat the patient, how to move the patient such that you hit the tumor? Well, basically you have to do matching between the two images. And we do that in 2 steps. First, we match the vertebrae, the spine, and then we match the tumor. So if I just go to a green-purple mode and I match the vertebra, then this is the automatic matching. So now the bones that we matched, you can see the patient is bent a little bit different, but the bones at the level of the abdomen are pretty much aligned. And this is driven by a region of interest. Then the next step is that you go to the tumor, and now I do the registration. And now I'm not doing a single registration, but I'm doing 10 image registrations, where I'm looking at every frame of my 4D movie loop. And then when the registration is done, the radiographer has to check 30 numbers, 10 registrations. Well, that takes forever. So you need a very simple way to do it. And the trick that we came up with is to grab the tumor and hold it in place. If the computer knows where the tumor is, you can keep it still. And the radiographer is looking at this screen and is checking whether the tumor is moving or not. If the tumor is not moving and it's in the red line, then the computer knows exactly where it is. And then let me zoom in a little bit. And then you can use that information to shift the patient to the right place and deliver the radiotherapy to the right place. So this system has been in clinical use now for 15 years, 2009. Yeah, that's 15 years, 16 years with 40. Okay. So CT guided radiotherapy is really the standard now, but there is also MR guided radiotherapy. And I just want to spend a few words on those. There are 2 commercial systems currently. There's the ViewRay system, which uses a low field magnet, and there is the Elekta system, which uses a high field magnet. And basically, the MRI here is is sitting close to the patient, and the radiotherapy is delivered through the cryostat, and it's amazing, but that works. And we're treating patients. People are treating patients all over the world, but also in Manchester. And I just have an example here, and it kind of shows you an issue with this kind of equipment. You know, if you provide a lot of information and option to adjust the treatment in much detail, you need lots of people to operate the machine, and the doctors that normally would be offline have to move to the machine. So I think this machine has a lot of promise, and we can do large treatments, but somehow all of the operations that are done in the machine need to be transferred over to the radiographers, and obviously people are looking into that, and we're doing that in Manchester, because this is a cervix patient that we see, of which you see the MR scan on the right on the treatment machine, and an adaptive radiotherapy fraction of this patient takes an hour, and that's absolutely not sustainable. But nice. Well, I also teach a little bit in treatment planning. I don't know very much about treatment planning, but treatment planning means that you place the beams on the patient such that the high dose gets to the tumor, and you avoid the organ at risk. And that is a very, very careful balance. And if you ask, in this case, 40 groups of people to do that, you can get 40 different treatment plans. And one of the causes of those differences is people put different priorities on the organ at risk, because you cannot spare everything. So you may need to make a choice. So what are you going to do? And one of the problems is that the dose constraints, the numbers that we use to say, okay, the lung may not have more than a mean dose of 20 gray, or 30% of the lung may not have more than 20 gray, or these kind of numbers. They are really kind of soft. There's not a lot of evidence behind them. So one of the things that we've been doing is we've been doing big data analysis, where we're looking at what actually happens during treatment, which is not exactly what you plan, because the patient is not lying still. There is deformation of the patient, and there's deformation of the organs, and that means that your treatment is not perfect. That's bad, isn't it? Well, it's bad, but it's also very, very interesting, because you can see it as a mini clinical trial. Let's put the patients on the bed, and for half the patients, let's move the heart a little bit to the left, and for the other half of the patient, let's move the heart a little bit to the right. That's not what you're doing, but that's what's happening. And that is like a natural experiment. And we had a student, Corinne Johnson-Hart, who looked into that, and she showed that those tiny little shifts of the heart were completely random. They were not correlated to any of the clinical variables, but they were correlated with outcome. Let's see that somebody wants to get in. And that was kind of a revelation that shifts in the order of a millimeter or a couple of millimeters could give a measurable difference in outcome. And that's shown here in the Kaplan-Meier survival curves, where you can see at about 1 year, maybe 10% difference in survival for a 1 millimeter plus or minus shift of the heart relative to the beams. That doesn't mean that our accuracy is not good. It means that our dose constraints for the heart are not right. And we've been looking into that in great detail. And almost 2 years ago, in a rapid learning study, we've started sparing the bit of the heart that we think is the most sensitive. And Pauline. Up to now, we have treated about 750 patients where we're sparing that bit of the heart, and that information is being collected and is being analyzed, and hopefully we will show a difference in survival. But the outcome is still blinded, but for the late-breaking abstract, we're going to analyze this data, and let's hope that we indeed see a difference and that our big data analysis has made a change. Okay. That brings me to my conclusions. So I successfully restored a Nova 1210 computer from 1972. I think it's nice to restore computers because it kind of teaches you how it works. And the older stuff is a lot simpler than the modern computers, but they're fundamentally the same. There's just a lot of terminology and bullshit that you don't want to know about, but it's just bits and bytes. And some computers are faster, some are slower. So I used the same algorithm that I used in my Common CT on the Nova, and I managed to reconstruct a single slice CT in about 1 minute. And obviously, computers have been instrumental to everything we're doing in medicine, but specifically in radiotherapy, which is very much a digital technique. And they have enabled image-guided radiotherapy with CT, with X-rays, with CT and MR to give a very high accuracy. But we are now so accurate that we need to know better exactly what we're going to do with all that accuracy. And that's why we moved into big data analysis to improve our knowledge of the dose constraints, so that we do the right thing. Yeah, we can put a dose anywhere we want, but we need to know where to put it. So obviously, I haven't done this alone. I've worked for 34 years in NKI, and they're all my colleagues there that I work with. And the last 10 years, I've been in Manchester, and this is our Christmas lunch last year, and that's wonderful. And I have a very vibrant group of researchers, and it's really a pleasure to work with all these young people. You know, it's sad to see them. It keeps you young to do the research and work with these people. And I definitely also want to manage Dennis, who is now managing my home during the demo. And let's see if the light is going to go out. So, and last but not least, I'd like to thank the family here. They've always been very supportive, and I hope they're listening now. And I showed you CTE reconstruction is very simple, but I was actually fighting for weeks with the code, and you see a bunch of bloopers there. Yeah, before it actually worked. This is what it looked like. Thank you for your attention. All right, and I understand that if you're online and you want to ask questions, you should put it in the chat. So let me just say that, and let's see if I can find this chat.
All right, thank you for doing my job. That was a brilliant lecture, so thank you so much. And I think we all agree your battling code was well worth it. So thank you for all that for being very into what's been a brilliant talk. And the history of the British Society of History of Radiology, it's interested in insight we gain from history. It's not about stamp collecting from the sake of it, it's about giving insight into where we're going in the future. And I think that's a brilliant illustration how understanding the technology and what's been involved as we move forward gives us a perspective of where we're heading next. So thank you so much for a brilliant lecture. We'll give people online a whole bit of an opportunity to type their questions in. But in the meantime, are there any questions in the room? Adrian.
Oh, that was absolutely wonderful. I've greatly enjoyed that, and I think particularly coming from Manchester, because you think of Manchester and Ralston Patterson and the Manchester survey, you actually see the service being treated now, and you sort of wonder what Ralston Patterson would have thought about that and how astonished he'd be. And also what Alan McCormack would have thought of him being a nuclear physicist and getting the Nobel Prize with Godfrey Hounsfield. Reconstructing old data on an old computer. What would happen if you had the original data from the early scan, which obviously is fairly primitive detection, if you actually analyze its data on a modern computer? What would it look like?
I think actually what Hounsfield and colleagues did was to make the scanner such that the signal was very clean. So by using a single detector, you had no detector differences, so you had no artifacts of that. He encompassed the head in a water bag, such that the head was round, such that the attenuation of the patient was pretty much the same from all angles. And he calibrated the whole thing by putting a water sphere into the scanner. So I think actually the images would look brilliant, and actually we know that they look brilliant because I reconstructed at 80 by 80 pixels, which is very rough. That's the clinical resolution, but all the published pictures are reconstructed at the double resolution, and actually they do show pretty much all the tumors and cavities and cysts that you want to see. So I think the images are very nice, and I don't think my reconstruction would do a better job than his at all. And he didn't need that because the design of the scanner.
Any other questions? No, or Scott, one, yeah, so, I, from online.
We can't hear the questions from the floor.
Okay, so, if you could recap the question, but it's just behind you, very much myself, what is the next big step in image-guided radiotherapy?
What's the next big step in image-guided radiotherapy? Yeah, that's a good question. Nobody really knows. You know, so we basically want to understand how the tumor and the organ at risk are responding to the radiotherapy. And I think a development that I find very interesting is to use your guided imaging, particularly the MRI, to do functional imaging of the patient. So to look how the tumor responds, how the normal tissue responds, and then potentially adapt the treatment to the individual patient based on that data. So biological adaptive radiotherapy, but it's easily said, it's very, very hard done. So I think that is several years in the future. You know, image guidance is actually just quite good. You know, it's not the limiting factor anymore. So the limiting factor is knowing what to treat and knowing what to spare to what dose.
Thanks. Well, I have a slightly cheeky question then, because with that in mind, if we've got to the point where the guidance is really pretty accurate, do you think that we're in a sort of law of diminishing returns where actually, given, because I've been doing work in sustainability, into this imaging technology that's very carbon heavy, is there a point at which we go, actually, this is good enough, and beyond that, we're actually, you know, it's sort of not worth the addition?
Yeah, so the question was whether we're doing too much, and especially in sustainable future, yeah, all the energy they're using is maybe wasted. It's very, very hard to do that. You know, you cannot go back from seeing to not seeing. I don't think that will happen anytime soon. What will happen and what is happening is that because we're seeing what we're doing, we know better what we've done. We can learn through what we've done, and we can optimize the treatment. And one way of optimizing the treatment is to go back in the number of fractions, and particularly the master have run a lot of trials in that. And really that in terms of sustainability, I think that makes a big difference, because also the patient has to travel less often. Also, the personnel has to be less. Well, there's still a lot of personnel, but yeah, the less fractions means you can do the treatment quicker. It's more efficient, and there are more patients. So we need to do more treatments with the same number of people, and I think that is something that is made possible. And I think these techniques where we are hitting the tumor very hard in a few fractions, they would have not been possible without image guidance. You wouldn't dare to treat a tumor in one go if you weren't absolutely sure that the tumor is there.
I'll possibly remember to recap.
Yeah, I will repeat the question.
Marcel, wonderful talk. It's so entertaining. Thank you very much. So this loads of multimodal imaging, we still don't use it for radiotherapy treatment. I mean, not. Oh, sorry, say it again. So we have lots of different ways of imaging the body,
Yeah,
particularly cancer. Why aren't we using multimodal imaging
for treatment planning?
Yeah.
Well, because okay, so we are, you know, we are definitely defining our tumor, looking at all the relevant scans, the PET scan, the MRI scan. So we're using it to a certain extent in treatment planning. And then the ultimate to use, for instance, PET scan in treatment planning is to say, okay, well, the tumor is very active in that region. Maybe we should give a bit more dosing. And people have tried it and tried it and tried it, and they all failed. So yeah, the imaging is brilliant, but we don't really understand what the imaging tells us. So I think it is a very, very long process to get to really utilizing all the imaging in that way. But any imaging or what you can feel or see about the tumor, you know, with your finger or with your eyes, all that information is used in treatment planning. It's not just an image and a computer. There's definitely a human driving it all. Yeah, and then so you're asking about functional MRI. Yeah, no, and then indeed, and and then, yeah, what characteristics are important? So there is currently a trial running in HPV positive head and neck cancer, where the dose is reduced to the regions that are not hypoxic, I think. Yeah, or no, it's not. It's using F-minus scans. And I'm very, very curious because reducing the dose where we don't need that much dose, I think that's a brilliant development. But it's also very, very scary. Okay, we have a question in the chat. Let me have a look. Repeat the question. Yeah, the question was about integration of different imaging modalities in treatment planning. Yes.
Sorry about that question. It's obviously very exciting seeing the providing this service in a well-resourced centre, high technology, but also our friends in South America and areas of the world, access to radiotherapy is really quite limited. And I think one of the things has to be is how do you apply such technology in areas which are actually less well resourced. So at what point can radiotherapy and this sort of technology be applied in a culture or a society which is not as well resourced as Manchester?
Yeah, so the question is, well, how are we going to provide radiotherapy to the less resourced countries in the world? And it's a really hard question. You know, one idea is to make the machines simpler and make trucks where we can drive them. What I know and I find very sad is that machines that have been delivered to lower income countries often can't be used because there are no spare parts. You know, so the maintenance is a big issue. The quality of the mains power is an issue. So it's not one that is easily solved. But yeah, simple is better in that sense. You know, simple system. So for instance, a modern accelerator has like 120 leaves that can shape the beam. It's complete nonsense. You know, if you shape the beam with 40 leaves, your treatment plan is 95% as good. You know, there is a lot of overkill, and then maybe we can get rid of that. But then you build a simple machine, and then people don't buy it because they want the real thing. So that's the curse of marketing, I think.